So this video is the continuation of the proof for the fundamental theorem of finite abelian groups that I decided to, following more or less the Galilean book, to divide into a couple of lemmas. So this video will be about the second lemma. So let G be an abelian group, because this is for finite abelian groups. Let G be an abelian group of prime power order. Okay, so G is an abelian group of prime power order, and let A be an element of maximal order in G. So no other element will have an order bigger than A in G. Then G can be written in the form set generated by A times K. Okay? Oh, what is K? We saw in the previous video that K is a set, actually is a subgroup of G. Okay? Equals the identity. It's quite easy to show that K is a subgroup of G. Okay, so let us provide a proof for this lemma. So A is an element in the group G, right? So A will be an element in the abelian group G, okay? And A is an element of maximal order. So what the lemma says is then G can be written in the form product between K, this subgroup, and the set generated by the element of maximal order. Okay, so we pick G and we see what the order of G is. So the order of G has to be a prime power order. Okay, so this has to be p to the power of n, where p is prime. Okay, basically what we are going to do is induct, or using induction on n, okay, which is not very hard. So if n equals 1, this is easy because G will be A times, so n is 1, right? So this x is to the power of 1. So the only element that to the power of 1 is the identity itself. So it would be A times the identity. Okay, if n is equal to 1. Okay, checked. So let us say that this is also true for G order P of a fixed K. Okay, well, of course K has to be smaller than n. Okay, so we go back to G. Okay, we go back to the group G and we choose an element A, where A is of maximal order. Okay, so that element will be x to the power of p. Okay, maximal order, what kind of order shall we let us say the maximal order, the element of maximal order as order p to the power of m. So x to the power of p, I'm going to write it down here. Okay, so this was for n equals 1. Okay, quick revision. So the order of G is p to the power of k, where k is less than n and k is fixed. Okay, now we go back to the group G. We pick an element A with the order Pm. Okay, so x to the p to the power of m, x to the power of p to the power of m will be the identity, okay, for all x in G. Okay, let us assume now that G is not generated by A. Okay, because if G is generated by A, is over. Okay, so we have the proof is finished. Because it's finished because then A equals to P of M. Okay, so it is proved. So it would prove that A generates the group. End of story. Okay, so we are going to assume that G is not generated by A. Okay, so we say that G is not generated by A. And let us go back to G and pick another element, an element that we are going to call B. But we want B not in the group or not in the set generated by A. Okay, what can we say? I say that the set generated by A, this element of order p to the power of n, intersected with the set generated by B will be the identity. That's what I claim. Okay, is that true? Well, yes it is, because we can prove that easily, showing that the order of this element here, of B, has to be P, the prime we choose up there. Why? Because the order of B to the power of P, the P we choose up there, will be equal to the order of B dividing P. Okay? And we also know that B to the power of P is, obviously, because B is not in A, but B to the power of P has to be in the set generated by A. Okay, just look at the way we choose B. Okay, now let us say that B, this one, to the power of P is equal. Now we have to give some order to A. Since it belongs to A, let us say AI. Okay, let us notice something first. The identity is going to be equal to B to the power of P to the power of M, right? As we choose up here, right? Okay, so this is the same as saying that B to the power of P, this P here, is the same as P, yes, P to the power of M minus 1. And that is nothing else. Since we choose B to the power of P as AI, we are going to say that this is AI to the power of P to the power of M minus 1. Okay, so we can easily say that the order of A to the power of I is smaller than P to the power of M minus 1. So since all this is true, we can easily say that A to the power of I is not a generator of the set generated by A. Okay, and now we use the previous theorem again to say that the greatest common divisor, I will show the theorem, p to the power of mi is not 1. Okay, what did I use here? I used this one, generated of cyclic groups. Okay, let G be generated by an element A, be a cyclic group of order n, then G, a to the power of k, if and only if the greatest common divisor of k and n is 1. So clearly here a to the power of I is not a generator of A, so the greatest common divisor of p to the power of m, this one used up here, and I cannot be 1. So we just proved that p divides I. Okay, so since p divides I, we can write this as I is equal to p times j. Okay, then we can say b to the power of p, please go back and check this, is equal to a to the power of I, and since I is equal to pj, we can say that a is equal to pj. Okay, now we are going to consider an element here, an element C. Okay, let us say that C is a to the power of minus j times b. Okay, it's obvious that C is not in the set generated by A, because if C was in the set generated by A, B would be also in the set generated by A, and that's not true. So here we are going to do the same. C to the power of P is going to be equal to A, we said minus JB, right? Minus J P, okay, B to the power of P, that's what we used up there, right? So this is equal to a to the power of minus I, that we use there, BP. Please just check the algebra here. It's really easy. Looks complicated, but it's really easy. B to the power of P, and this is nothing else but the identity. Okay? So what happened here? Well, we found an element C, this is the element C, okay, of order P, okay, C of order P, and C is not in the set generated by A, okay, and since the other one we chose B was the smallest order, remember that we picked a B that was the smallest order, not in A, we conclude that B has also the same order, so the order of B is P. Okay, so the order of B is P. Remember, we claimed that the order of B was P. Okay, so that's exactly what we just proved. Now, to finish, I'm going to use Galilean notation. We are going to consider a factor group that I'm going to use this notation, where G is the factor group by the set generated by B, this B that we just got. Okay, to simplify the notation, I'm going to call X bar the coset X times the element B, the set generated by B, all this in G bar. Okay? Okay, if the order of A bar is smaller than the order of A, well, the order of A is P to the power of M. Please check it before. So then, if this happens, so a bar to the power of p minus 1 is going to be the identity bar. Okay, what does that mean? This means that a, so the left coset of the set generated by b times a to the power of p to the power of minus m minus 1 is equal to a to the power of b minus 1. This is simple algebra. This one you don't need the power because b will be b, okay? Doesn't matter how many times you factor this, b is b, okay? And this is nothing else but the set generated by b. So this one, a to the power of b to the power of minus 1, is in a intersected with the set generated by b, but that means that that is the set, the singleton with only the identity. Okay, so this contradicts the fact that the order of a is b to the power of m. Okay, so the order of a bar is equal to the order of a and is equal to the p to the power of m. Okay, and so we can say that a bar is an element of maximal order in G bar, because we have been here in G bar. Okay, since that is true, so now we are going to use induction again, because we know that G bar, this G bar here again, this G bar can be written in the form of set generated by a bar times k bar. Okay, and this is for subgroups k bar. K bar is a subgroup of G bar. Okay, so now we have to pick. We have k bar, but we have to pick a careful k here. Okay, let us say that we get k from k bar, okay, with what we called in the previous video a natural homomorphism. Okay, you get the natural homomorphism from G to G bar. Please check the previous video for that. Okay, so what is k? K is going to be x in G such that x bar is in k bar. Okay, now we say that since this is true, we say, and this is a claim, that the set generated by A intersected with K is the identity. Why do we say that? Because if X is an element in this set, A generated intersection of A generated by A intersection with K, if X is here, then X bar has to be in the correspondent set. Okay, A bar set generated by A bar intersection with K bar. Okay, that is equal to the bar identity, A bar. But all this is the set generated by B. Okay, and since X is in the intersection of A with B, so this will be the identity. Okay, so now this is really basic. It's only the what we call the order argument. It's a matter of order. Okay, so G has to be equal to the set generated by A times the subgroup K. Okay, and that means that G is equal to the set generated by A times K, and this concludes the proof.